Okay, let's start. And yesterday we started to talk about fusion category, maybe braid fusion category, or quantum dimension, those kind of things, fancy abstract mathematical stuff. And but why we want to do that? Because we want to study a Hamiltonian with some kind of ground states, but this ground state have some entanglement structure, so called long-range entanglement. And we try to measure this entanglement structure, try to probe those entanglement structure. It's kind of like when we have a crystal, we want to measure crystal structure, we do X-ray scattering. But suppose we do not have X-ray scatter, we don't have X-ray. So how do we measure crystal structure? So one way to do so is to consider dislocation of some other defect in a crystal. Then all those defects and their property can be used to measure crystal structure. So actually, this is kind of interesting question. I don't know whether how much people study that. We just pretend we don't have a X-ray, and how to use a defect and what property defect should we use so that we can fully characterize the crystal and the space group. So that's kind of interesting question. And here we are doing similar thing. We want to study the entanglement structure. But how to describe entanglement structure quantitatively? So it seems difficult. And here we study defect, means we study punctures created by the traps, and then study the property of those punctures. Okay. Then here we try to describe what kind of property we want to study. One property is this equivalence class. How many different equivalence class do we have? Means how many different type of a puncture can we have? Certain different type is defined by this by adiabatically change this trap. If two trap can be changed to each other without closing energy gap, we say these two traps are equivalent. The equivalent class of a trap define the particle type, and how many equivalence class of trap. That's already a very important data for entanglement. And then we can study the fusion. When you view two trap as one trap, you know how this equivalent class merge. So we have this fusion ring with Nijk describing this fusion ring. Then that's another data to describe the entanglement structure. And then from this Nijk, this fusion coefficient, we can compute the so-called internal degree freedom for each excitation of quasi-particle. And that gives us concept of quantum dimension. So slowly we're using some physical measurement of physical tools to extract some data. And those data actually is a fusion category or modular tensor category. So those data form those categories. And so this may be the most mathematical part of this talk. It's a sequence of talk. So actually, not only we have this fusion ring Nijk, we also have this so-called F symbol. Actually, we know about F symbol in the group theory. We can fuse two group representation into some other representation. And then, but however, when you have three representation IJK to fuse together into representation L, then there's an order. We can fuse JK first or first IJ first. And then when fusing this different order, the decomposition have some relation. And this relation between these two different way to fuse or to decompose is called the 6J symbol. And remember that our particle, the fusion space is given by those particle III. So you can view this then we try to view this fusion space as an individual vector space tensor together. It's in a sense, we try to we try to think each particle have internal degree of freedom, and this internal degree of freedom is like a vector space, just like a group representation. The vector space tensor product two vector space, you get a tensor product of group representation. You always try to think this way, even though this vector space don't even have integer dimension. Okay, but you can still think that way and formally, and that's what a mathematician do. And so therefore, this stick-JS symbol can be defined formally, even without knowing or seeing internal vector or vector space. We just formally have something we call vector space. So this IJK can be thought as some formal vector space. It have internal degree freedom labeled by the quantum dimension. Okay, so maybe just one explain one line. So suppose we have IJK, that's a trap or quasi-particle fused with some other things to get some fusion space. So this V just is a grounded subspace with many traps. Okay. However, if we try to bring IJ close together, like in this case, if you bring IJ close together, then this the degeneracy. So this big bar is this V may split into some subspace. So this subspace is really this labeled by M. But also, but for the same M, there may be M may appear several times. So we have alpha. Alpha label, if M appears several times, then this different time again labeled by alpha. So several copy of this M subspace then labeled by alpha. So therefore, this original space can be written as the direct sum of some smaller space. This smaller space is just this smaller bar here. And then we can fuse this combination IJ combination, which became M, fuse M with K. Then each one, so this one do not split, but this one split, and the last one also split. Then we get a further smaller, even smaller space. So basically, is that this original vector space can be decomposed into direct sum of those smaller space. And this can decomposition very much like choice basis vector. The basis vector can be viewed as a one-dimensional vector space. And choosing a basis vector is basically write a vector space as a direct sum of several one-dimensional vector space. So we view this choosing basis vector is really choosing the decomposition, choosing a direct sum decomposition. So therefore, this order of fusion gave us a particular direct sum decomposition of the original big vector space. That's a grounded subspace. Then certainly we can do another fusion. We can do fuse JK first and I with a N later. Then it gives us another direct sum decomposition of same vector space. So therefore, these two direct sum decomposition like choosing two different bases, and they're related by a unitary transformation. And this unit transformation is this F symbol. So basically, so the formula is that this particular basis vector can be written as a superposition of some other basis vector. So that's the way I look at it. So therefore, actually, the F symbol is there. It's kind of tricky to see it's there, but the fusion ring is easy to see. It's physically more transparent. But F symbol is more subtle, but it's there. It's important data. Okay. And this F symbol is some matrix. So basically, this matrix labeled the IJKL. And the index matrix, this is a row index, this is a column index. So there are three indexes, a combination describe row and column, basically. And this one is a unitary matrix. And the F symbol cannot be arbitrary unitary matrix. There's a very famous constraint called the Pentagon identity. That is when you try to fusing four particles. Then from this wave of fusion to that wave of fusion, there are two different paths. What I try to say that this order fusion and that order fusion also related by a unitary matrix. But this big unitary matrix can be viewed as a composition of a F symbol, which is smaller unitary matrix. It's really just like that. So you can see to go from here to here, we can fuse let me see. Okay, yeah, we can switch the fusion order. So here the K fuse first with this with M here, but then we choose switch order. We say K fuse with L first. So from here to here, they differ by the F matrix because the order for fusion K is changed, and that's related to the F matrix. So basically, I'm really using this graph. So this graph and this graph are related by this F matrix. Yeah, the changing basis. And then we can bring the J fuse is I first here. Then we say J fuse with a Q first. Again, the switching order. So that is another F matrix. Yes.
Elementary question: What is alpha? Greek letter symbol.
Oh, that's a degeneracy. Yeah, you can see here we have alpha beta. You see, where does alpha beta come from? This Mn is just a Ij fused into M or Jk fused into N. But what is alpha? Alpha appear here. You know, here we have Ij fused into M, but M may appear several times. That is correspond to the situation where this where the Ij fused into K1, K2, K3, etc. But maybe K1 equal to K2 is same type. So this K1 may appear twice. Then we have Nij K, that's K, the N would be 2. So when you're writing out the direct sum, the K would appear twice. Yeah. And so here's the same thing, you know, if Nijm is more than 1, then alpha would have a range from 1 to this value. That means that this M appears several times. And we put that index of how many times M appear at this vertex. So Ij fusing to M, but M may appear several times, this alpha may have a range. If M always appear once, I mean, Nijm equal to 0 or 1, then we don't need this index at the vertex. Yeah. That's a simpler. And but in general, we somehow need this index.
So can I follow?
Yeah.
So script V is the fundamental mathematical object, and everything else. If you know V, then everything else can be extracted from it, like these numbers.
Exactly.
No. Sorry.
Yeah. Yes.
Okay.
Yeah. So since you asked this question, so maybe we can just go here. So the ground state subspace of a trap is this script V. It's something accessible physically, and that corresponds to infusion category is a home space from Ij to identity to trivial. So this is the physics. You know, physics only this home space accessible, and then we try to construct this everything else from this home space. In usual mathematical theory, the home space is not that order. They have other thing beginning. Then at the end, you get has a home space. So this is an interesting way to look at the fusion category or tensor category. That's if only home space is a physical measurable, then we define out the concept the category from the home space. So actually, this what I'm trying to do here is it's just like that. And similarly, we can go from here to here in different order. We can switch in the J first. So J first to the J first fuse to the right, left. Then we fuse to the right. Then we can switch in this T then and etc. Then here, but we need to take 3 steps. So we have 3 F symbol to go from here to here. But the first pass is a 2-step 2 F symbol. So this is just 2 different ways to express the same unitary relation between this choice basis and that choice basis. So we should get the same results. So that's a huge equivalence relation. That's a constraint. That's this F symbol should satisfy this Polygon identity. It's nonlinear algebraic equation. And that's almost it. That's how I view module or fusion category. Fusion category is described by data Nijk and F symbol. And Nijk satisfy this kind of condition, and the F symbol satisfy this Polygon identity. There's a few other not so important relation. And solving those, we get a so-called allowed legal data. And that is a fusion category. So that's a kind of computer understood the way to define fusion category. But in my book, the fusion category defined in a much more abstract fashion. Here is a one poor man's way to do so. Yes.
This elementary. Is this pentagon identity different from associativity in group?
It is associativity. Exactly. We can say
it looks not three.
Okay, yeah.
Consistency.
It is the F symbol is associator. You can see we fuse IJ first or fuse JK first, and they are related. It's kind of associator. It's related to associativity. And this Polygon identity is consistency condition on the associator.
What is the corresponding quantity in group theory? Group theory
F symbol is a 6J symbol.
I see.
Yeah. So actually in group theory, people compute the 6J symbol. And then because in group theory, we know this V, this vector space, this IJ, K are just vector space. And we know when they fuse, we know how they are related. So we compute 6J symbol. Then we find that this 6J symbol have this property. So therefore, the Polygon identity is a property of 6J symbol. And now we turn things around. We say we don't have a vector space. We don't know how to do this 6J symbol. But we're using Polygon identity as a defining property. That's define the fusion formally. Even though without vector space, we can define fusion formally. And so this is what you need to have a formal fusion. Yeah.
So in known examples, so do you really solve this pentagon equation, or you just calculate them from the V alpha? So
Yeah,
which one is practical?
You ask very good questions. Yeah. So it's making me like doing all this for nothing. So yeah, this is a theory, is set up, but at the moment it's useless. We cannot solve it. It's just a nonlinear algebraic equation. We just do it. Even for simplest case, because you can see how many labels we have. This F symbol have 10 labels. Each label have a range 2. That would be 1,000 unknown. And then this equation also have a lot of free index. And if each index have a range 2, maybe the 10,000 equation. So there are 10,000 nonlinear algebraic equation with a 1,000 unknown. It's overdetermined. Even for the simple case, and almost impossible. So there's a big industry. So I know is that try to find fusion category without solving this equation. So like using group theory, or some quantum double, or quantum group, and there's all kind of representation. Okay, representation of half algebra. So there's all kind of way one try to try to solve this without solving it. But by construction for that one. But we really wish there's a way to direct solve it. You can get classification, because it's very hard to solve this. So we don't have a classification of this fusion category. Yeah, there's upper bound. So for every there's a rank. Rank means how many how many type of particle do you have? The upper bound go. It's a very bad bound. It's billion, trillion, or billion of billion. This kind of bound, for small rank. Yeah. But it's yeah. However, things getting better if you for the braid fusion category. Fusion category is a lot headache. Okay. So what? And so here I want to say that this F symbol actually define a theory for one-dimensional excitation. Okay. It's a little surprising why I call this, because the way we do it is even though the picture I draw is you can see it's on any space, but when we actually compute and we can put those excitations on the line, and we do not switch their order. So all this calculation is done without switching their order. So therefore, this calculation works at the 1D. Certainly also works for a higher dimension. But in higher dimension, we have more structures. There's a more structure because the particle you can switch their order, you can break. But in one dimension, we cannot break. We can fuse. We can do fusion. And the fusion without switching order. And actually, this is exactly what we did so far, is fusion without switching order, all kind of thing. So therefore, this theory describes excitation any dimension, including one dimension. But however, in higher dimension, we have more data, more things. But in one dimension, that's all. Yeah. In one dimension, that's all the data. So this is why I say this kind of fusion category theory is actually a theory to describe one-dimensional excitation. And I hope including all the data for the one-dimensional representation is a complete description of a one-dimensional excitation. No additional data is needed. Okay. So this became really exciting. That is we have a mathematically consistent theory for one-dimensional excitation. Then physically, can we design the Hamiltonian in 1D lattice model, which have a gapped ground states and whose excitation happen to be reproduce this fusion category? Then we really have a story. Yeah. So almost like this extension is highly non-trivial. It's kind of like onion in one dimension or some topological in one dimension. Do we have that? Then you may say, well, we talk about this one-dimensional topological order since we conclude that there's no non-trivial topological order in one dimension. So what's going on here? So yeah. So before maybe before I go into that, let me just mention that yeah. So this fusion space is a ground state subspace is a fusion space in a category theory, and there's a lot of correspondence. I just say this in category theory we have an object, we have morphisms between object, we have simple object, there's composite object, and there's a fusion ring and the quantum dimension and etc. And they all here we just all have correspondence. The object actually is a trap. Object is delta H. But however, is the equivalent class of delta H to be more precise. Okay, and then this the morphism is really our unit transformation. You can maybe this unit transformation means like a adiabatic change of delta H. We'll change delta H adiabatically. You know this ground state subspace rotate related by the unitary matrix, and this unitary matrix is a morphism. You know. It's like an operator act on the topological excitation, local operator act on topological excitation. And if this is trap, if ground subspace is stable against the perturbation, this is called simple object. And the bound state of excitation is a fusion, you know, things like that. So therefore, this the notion in the category theory can be produced by this physical setting. Yeah, that's a message. And then we say that the unitary fusion category classify the allowed one-dimensional topological excitation. Okay. But whether they classify one-dimensional topological order, answer is no. The problem is following. If this fusion category is non-trivial, it's not realizable. Only trivial fusion category is realizable. Non-trivial is not realizable. So it's again, like we try very hard and get nothing. So somehow mathematics allow this kind of structure for one-dimensional particle. But the mathematics allow the structure cannot be realized by physics. It's a little bit surprising because we thought if something allowed, it should be realizable. Yeah. And so therefore this we can imagine the fusion category is like a quantum field theory. It's describe a low energy effective theory. It's like quantum field theory. So basically here we say that the fusion category is not realizable, like to say the quantum field theory have no UV completion. Yeah, using that language. And so this abstraction to find the lattice realization of quantum field theory or anything or modular tensor category is called a gravitational anomaly. Yeah, this is another definition of a gravitational anomaly. Usually the gravitational anomaly is defined as an abstraction to go from classical theory to quantum theory through path integral, because the passing measure is not diffeomorphism invariant. And here we define gravitational anomaly not as abstraction to go from classical to quantum theory, but as a property of a quantum theory itself. And then we say that there's a low energy effective quantum field theory which do not have any UV lattice realization. And this property is called a gravitational anomaly. And maybe we should call this a different name, but actually these two properties are very close related. So we can call the same name, but definitions are very, very different. Yes.
When you define local lattice model, do you mean that any interaction should be on site?
Short range interaction, not on site.
Not on site.
Yeah, short range.
Short range is not
Short range, yeah. Finite range.
Oh, only for
Yeah.
one. Okay.
Interaction have finite range.
Okay.
Yeah.
For any finite range, you can say it's local lattice model.
Yes.
Okay.
Yeah, local lattice model means you finite range.
Okay.
To be safe, we don't include the algebraic tail.
Okay.
Yeah, but that's be kind of shuttle thing. Yeah.
Okay. Thank you.
Okay. And so in some sense, we say that the unitary fusion category as a 1+1D quantum theory is anomalous. Yeah. So it's not reliable, it's anomalous. Okay.
Question.
Yeah, please.
So your local lattice model, does it include the anyone chain, like the Parfirmian chain, or like
Yeah, thank you. No. This lattice model is when I say lattice model, we have this definition of there's a vector space per site, and total vector space is a product of the tensor product of those small vector space.
I see.
So the lattice model have that more precise definition. Basically, the total Hilbert space have a tensor product decomposition, and each lattice site have a small vector space.
Mm-hmm.
Yeah, that's that's how we define the lattice model.
You don't allow the like infinite dimensional local Hilbert space either.
That is a really interesting question. Yeah, at the moment, no. But when you allow infinite dimensional on-site Hilbert space, it may become more powerful. And how much powerful? Yeah, that I don't know. Yeah, that's really interesting. Yeah. But here the lattice model, the on-site Hilbert space is finite dimensional. Yeah.
Okay. Thank you very much.
Yeah. So that's how we define this. Okay. And yeah,
In
question,
the
yeah.
previous page, so frankly speaking, I don't have any. I think I did understand. So, why this 1D theory has such an anomaly? Can I have some picture?
Well, it's falling. Let's use field theory. When you write down the continuum field theory, actually the continuum field theory can be more flexible, allow more things. And then you can write down the very ordinary looking continuous field theory. But then you realize that this continuum field theory cannot be realized by lattice model. Like when you have Cairo-Fermion theory, then there's no lattice description, realization for the Cairo-Fermion theory. But as a continuum field theory, it's okay. So what I try to say is that sometimes when you write down the macroscopic low energy effective theory, the consistent condition is more relaxed. We can write down seemingly consistent theory in a more flexible way. But writing down those reasonable theory may not mean it's realizable by lattice or by some UV completion. So this is typical tension from continuum to UV completion, and this mismatch from continuum consistent theory to consistent lattice UV completion. This mismatch is called anomaly. And this mismatch exists. That here just say this exists. So you can see what we did here is that we using some macroscopic consideration, define a self-consistent theory for one-dimensional excitations. It's like defining a field theory in the long distance. And then we ask next question: is this a self-consistent field theory are really consistent at the lattice scale? The answer is no. I cannot. Yeah, I don't know how to say more than that.
It has nothing to do with some lattice space group or blah blah.
No, there are no space here. We have a lattice
I mean,
model.
on the lattice. So when continuum field theory try to put such field theory on lattice, so sometimes we should consider some lattice space group blah blah. But this has nothing to do with that kind of.
No, yeah. Yeah, it's not related to symmetry. We don't need a symmetry. The lattice can be random lattice, random ground.
Any simple example to you? Example for this? Do you have any?
Okay.
If you take some time, you don't have.
Yeah, I have example. Maybe I have example later. Just maybe let me just discuss some example later. Yeah.
Can I sorry, one more question?
Yeah.
So the Haldane spin one chain, you wouldn't classify this as a topological phase.
No, it's not topological phase. It have a symmetry.
I see.
So far there's no symmetry. There's no global symmetry. When I say lattice model, we don't need a symmetry. And in this in the trap Hamiltonian, no symmetry. So this spin one chain, if you don't have symmetry, that's a trivial phase. Yeah, it's belong to trivial product phase.
So if I think about SPTs, you definitely do have one-dimensional example.
For SPT, there always have symmetry. If you don't have symmetry, there's no SPT. So here we have no symmetry, so there's not even SPT.
So yeah, that's what I meant. If I sharpen this to think of the cases where I do think about,
you do have symmetry, yeah, then you have something.
then you have plenty of 1D examples.
Exactly.
Okay.
That exactly. Actually, my example will be along this direction.
Thanks.
When you add the symmetry, there's a you start to have something. Yeah.
So is there a possibility to realize non-trivial UFC on the boundary of hierarchy?
Yeah, that's the next slide. Yeah. So I try to explain anomaly from more general. You know why this theory have anomaly? The anomaly and related to this principle of remote detectability. So it's really the following. Imagine a soliton in field theory. There's two types of soliton. One type of soliton can be detected at infinity. We don't need to go close to soliton. By starting far away from soliton, we can detect that, like a monopole or vortex, we can detect that. And there's another soliton, like in non-linear model, you can map space with non-trivial homotopy group, wrap the target space. That soliton is really local. From infinity, we have no sign of such soliton. And so this topological excitation we talked about is kind of like a soliton, like topological thing. But this belongs to the first type. I mean, like monopole or vortex, and they should be detectable at infinity. And the reason is that if a soliton cannot be detected in infinity, like you will just wrap space locally to some target space. Because we have a lattice model, there's no continuity. So this kind of soliton, although we call topological, it has non-trivial wrapping. Once you have a lattice, you can always break continuity and unwrap it. So that soliton is like a local, can be created by local operators. And only when you have a non-trivial structure at infinity, you have this non-trivial particle topological extension. So that's really, this is really trying to say that somehow there's another requirement I didn't put in. That is the topological extension should be detectable remotely. You know, in a reasonable realization, this topological extension should be detectable remotely. And if that happens, it can be realized by lattice. If not, then it's not realizable by lattice. So in a sense, we can say that one way to probe remotely like a braiding. Now particle and another particle is detector. Then you braid around the first particle. You see the phase. This mutual statistic is like a remote detector, like detecting the magnetic flux of vorticity, and to say, yeah, this is a topological soliton which have non-trivial structure at infinity. But in one dimension, we cannot do braiding. So there's no room to do braiding. Okay. So therefore, this topological in one dimension, they are not detectable remotely. There's no such a remote detector. So this is the reason that in higher dimension, because we have braiding, this particle non-trivial particle extension is consistent. But in one dimension, whenever we have a non-trivial particle extension, then it's not remotely detectable. It means anomalous. So basically, say remotely detectable and anomaly free. We try to say this is the same thing. And if the topological extension can all be remotely detected, then it's realizable by lattice. Otherwise, it cannot be realized by lattice. Yeah.
So is it true for only the gravitational anomaly, or I mean, does it include other kinds of anomaly?
At the moment, we don't have any symmetry. So that's only for gravitational anomaly. And when you have a symmetry, this thing is no longer true. Yeah. Yeah, this is only for gravitational anomaly. The symmetry is different. Yeah. So this is a kind of a more physical reason to say why one-dimensional fusion category is kind of anomalous. It's not realizable. It do not exist. While we talk about it, then it's this. It is consistent. It must exist. So I always say it's not exist, but it must exist. But in some way, exactly what you mentioned, is realized a boundary. You know, it turns out that this even though it's not realizable by one-dimensional system, but realizable as a two-dimensional or two-polarity lattice model with energy gap. Because the fusion category is a low energy theory. If your bulk have very large energy gap, in boundary you don't see them. So it's okay to attach a bulk with a very large energy gap. It's very much an anomaly inflow. Once you say this one-dimensional fusion category is anomalous, then it's very natural to think, oh, anomaly inflow, there should be non-trivial bulk. And this non-trivial bulk is really the topological order, bulk topological order. So actually there's so if in one dimension is normally free, then the topological order in the bulk is trivial, then you don't need the bulk. Because trivial topological order means the product states. The product state, you can remove the product state, then you don't need the bulk. However, if topological order in the bulk is non-trivial, even though it have energy gap, you know, usually when something have energy gap, so we can throw them away. But because there's an intrinsic Lagrange entanglement, we cannot really throw them away. Then their boundary would have this gravitational anomaly. And here I want to say that this gravitational anomaly is a generalized gravitational anomaly, because the gravitational anomaly people talk about usually means invertible one. And however, the topological order in the bulk is usually not invertible. And so therefore, this from this bulk boundary relation, using this to define gravitational anomaly, most gravitational anomaly are not invertible. So I'll come back to the invertible things later. Yeah, but just say this generalized one. Okay, and so therefore this n-dimensional anomaly and n+1 dimensional topological order are really have this we try to say have one-to-one correspondence. Actually, almost they are same thing basically. Yeah, and so this is a kind of a classification of a gravitational anomaly because we are not talking about symmetry.
Sorry.
Yeah.
About this gravitational anomaly, is this, if I think in the continuum, is this just C left not being equal to C right, or is it more general?
Much more general.
So like the 2/3 state has this anomaly.
You know, any two-dimensional topological order is boundary would have that type of anomaly.
Okay.
Because what you describe is a chiral center charge.
Yeah.
It's just one feature. But there's many different topological orders, many different patterns. So any module tensor category is a gravitational anomaly in one lower dimension.
But this would have something to do with whether or not you can locally gap the edge states. Is that
no, that's one. Yeah. So for a lot of gravitational anomaly, you can gap the boundary. You can gap the edge states. Yeah, there are certain gravitational anomaly. It's more. Yeah, it's
more general.
Yeah, it's more wild. Let me say. Yeah, the boundary has to be gapless. Yeah, and okay. So that's a kind of a bigger picture now. And let me just go quickly. That so that's about one dimension. In two dimension, as I mentioned, we can do braiding. And as a result, you know, fusion ring, this Nijk, Nij will be equal to Nji. You know, even before we don't assume this they are symmetric. Even non-symmetric is okay. But most solution is symmetric, but there are indeed non-symmetric solution. But in two dimension, Ijji is a same bound state. So this one is symmetric. And most importantly, you can braid. And the braiding related to the R matrix is, so I'm not going to talk about R matrix. It became more technical. But only I want to talk about this one thing. Not when you braid twice, the R matrix describes half braiding. You just exchange. But if Ij are different exchange, you know, get different configuration is you don't have definite phase. But if you braid twice, it's like doing this mutual statistic. You should get a phase. And something easy to understand is that we got theta Ij. Theta Ij just means the mutual statistical angle between I particle and the J particle. There's a little bit of twist. Usually when you say we have two onions with the mutual statistics theta Ij, that's it. But here, this Ij may fuse into K, maybe several different K. It turns out that depending on fusion channel, this phase factor may be different. So this mutual statistical angle not only contains theta Ij, also have a K dependence. And that's it. So this, I think this is a good data. It's easier to understand than R simple. So one can using this data to describe this mutual statistics, the braiding. Okay, then we include the braiding. Then this is three tensors. Now we have R tensor, or this is theta Ijk. Would define so-called unitary braid fusion category, and they are theory for two-dimensional excitation. Yeah, so it's very similar. Then in three dimension you can do similar thing, but in three dimension there's more. You may have a string excitation. Yeah, and then actually there's one thing. In two dimension we can have a string excitation. Why we only consider particle? Indeed, we in general we should have string excitation. So the most general theory for two-dimensional excitation, including both particle and the string. Here I consider some kind of a simplified one, but for the reason, because here we have more intention that we hope our theory are realizable by lattice. When you have a string, the string cannot braid, just like in one dimension, the particle cannot braid. In two-dimensional string cannot break. The codimension one defect cannot break. So if you have a codimension one defect, then they bound to be anomalous. So we remove string from beginning. And once you have string, it's anomalous. It's not realizable. But without string, this kind of braid fusion category, it may be realizable. So that's a question. Whether they are realizable or not. Okay. Again, no. And so we have the same issue. There's a braid fusion category describe a consistent braiding and fusion for particles. But however, but not all the braid fusion category are realizable by lattice because of anomaly, same reason. And here we can describe anomaly more easily. That is, sometimes we have we have particular particle, and this particle cannot be detected by braiding with any other particle. If that happens, it's anomalous. So we have this undetectable particle. This anomalous. So this feature is called the degenerate. You know, if you have undetectable particles, this braid fusion category are called degenerate. If only trivial particle is undetectable, then every other particle detectable, they call non-degenerate. So that's a mathematical term for this. So therefore, remember we described topological order using ST matrix. If you know the S matrix, you can compute this what is detectable, what is not detectable. But anyway, I won't go into detail here. But it's from here we just want to say that some braid fusion category is detectable, some anomalous, some is not. And the non-degenerate one is called a modular tensor category. Okay, so braid fusion category is more general. It could be degenerate. And the modular tensor category is a subset of that. And then it satisfies this remote detectability. It's normally free. And they are all realizable. The modular tensor categories, they're all realizable. At least that's a conjecture. We think they are all realizable. Yeah.
Is there any issue the lattice model loses locality? Is there any issue if a lattice model loses locality?
If a lattice model loses locality, there's a lot of issue because we don't have a dimension. When you have a non-local interaction, you are thinking of a zero-dimensional system. So the property here depends on dimension a lot. And so there's a local unitary, and this when you do braiding, there's notion of doing things slowly. When particles are far apart, they all require this locality. Yeah, without locality, doesn't work. However, if you say interaction decay with certain large power, this may work, but that's a bit more detailed thing. Yeah.
Can I ask a question?
Yeah, please.
So in the 1D models, you said Unterberg UFC cannot be realized. And maybe it's a stupid, and I think I misunderstood a little bit, but yeah. Can you comment on the Majorana zero mode and the type chain, because it has a local space and local Hamiltonian, but it looks like I can still have some non-trivial excitation.
You mean? Okay. The first we talk about is a bosonic system. We are not talking about the fermionic system here. That's very important. And boson fermion have totally different picture. Yeah.
Yeah. Then
yeah,
then
and
fine.
yeah, the Kitaev chain you can map to bosonic system is a symmetry breaking state. So
Right.
it's a symmetry breaking. Yeah.
I see. Thank you.
Yeah.
So when you say realizable by a lattice model, you mean lattice model in the same dimension?
In the same dimension, yes.
Okay, but when the MTC has a central charge, isn't
It's
it
realizable.
still realizable?
Yeah, yeah.
Okay.
Yeah, this is a very interesting question. Yeah. And when MTC have central charge, and the mathematical thing is not realizable. The physics thing is realizable. The difference is the following. When MTC have another central charge, it's realizable by by a model which we cannot solve exactly. And then we have some kind of hand-waving way to solve that numerically. And you know, even with 10% error bar, we think that's convincing enough to so it's there.
Right, so
But however, it's not rigorous. So we have a 10% error bar, probably it does not exist from mathematical point of view.
But there is no general construction like the Levin-Lam.
No, yeah. This is the commuting projection model always have a zero central charge.
Right.
Yeah, and I think, I don't know, there may be some kind of argument or proof that there is no commuting projector realization.
Oh.
I think that's almost a proof, yeah.
Okay.
And then it became big headache. You can propose the lattice model, you claim it's realized this particular MTC,
Yeah.
but it's very hard to confirm.
Okay.
Yeah,
But it's a case by case.
Yeah, it's case by case. But we know we have a lot of examples like quantum Hall states.
Yeah.
All given, right? So Chern-Simons theory is MTC with non-trivial central charge.
Right.
And but why quantum Hall states describing this Chern-Simons theory? You know, is numerical evidence, but numerical evidence only for the system maybe 20 electron.
Okay.
Yeah.
By the lattice model in that case would just be a lattice version of Chern-Simons, or
that's also an interesting question. The lattice version of Chern-Simons theory is very hard to define.
right.
and also for the good reason, because Chern-Simons theory is have chiral central charge.
Right.
A nice lattice model better to be commuting projector. Otherwise, a mess. You know,
Right.
we still don't know what to do with it.
Okay, so we believe there should be a lattice model, but it's not
So
clear.
the physics believe for every MTC there's a lattice model may not be
Right.
that soluble,
Right.
and to realize that.
Hmm.
And for the particular, yeah, this is a very good question. For some particular modular tensor category, which allow gap the boundary. Okay.
Right.
Then there is this the gap the boundary are always described as unitary fusion category.
Right.
When you have a unitary fusion category, you can construct string net, and then there's a commuting projector realization of this all MTC with the gap the boundary.
Right, but that's equivalent to having vanishing central charge, right?
Hmm?
Well, but that also requires that the central charge vanishes.
Yeah, that's
Right,
where central
right.
charge happen. Sometimes even when central charge vanishes, a certain MTC don't have a gap boundary, and we have similar
Oh,
problem.
then so
Yeah.
it's really not the central charge, but
It's a gap the boundary now.
Yeah.
So the non-understanding is that for all the MTC with the gap the boundary, there's a exact solid model to realize it. For those without the gap the boundary, we think there's a realizable, but that's a more physicist belief.
Okay.
Yeah. So here's some example. You know, the simplest anomalous unitary Brady fusion category is this: have two particles, trivial particle and the E particle. The E particle have a fusion of Z2 fusion. E and E became trivial, and the quantum dimension 1 and 1. The topological spin is 0. They are boson, so carry no spins. Okay. And and this one is anomalous because you can see that using topological spin, I think we can construct a theta ijk. Theta ijk, if I remember correctly, something like that. It's Si plus Sj minus Sk. Yeah. So if you know the topological spin, you can construct this mutual statistics. And also, if you from topological spin, you also have a self statistics. You know, it's just the self. There's spin statistical theorem. This self statistics also described by spin. If spin equal to integer is a boson, half integer is a fermion, other spin is an anion. You know, something like that. So therefore, I just using topological spin to describe a self and mutual statistics, and so that's what I'm here. So if then this topological spin equal to 0, that means they have trivial mutual statistics is not remotely detectable, things like that. So what? But you say this is realizable. You can say when you have a system with a Z2 symmetry, this E is Z2 charge, and this Brady fusion category really describing a system with a Z2 symmetry. And E is topological in that sense. You cannot destroy E by Z2 symmetric operator, but you can destroy it using Z2 symmetry breaking operator. Yeah. But we call this is anomalous because it's not realizable by lattice model without symmetry. Yeah. Because for lattice model without symmetry, this is also very strange because lattice model with symmetry is a special case of a lattice model without symmetry. This sounds very strange. You say when you require symmetry, it's now it's realizable. When you don't require symmetry, it's not realizable. But with the symmetry, special case of without symmetry is certainly realizable. The problem is the notion of a non-trivial excitation. Because non-trivial excitation is defined as a equivalent class of allowed perturbation. Allowed perturbation is changed. For model without symmetry, you have a large, you allow more perturbation, then you don't have two classes, you have one class. Then for the model with the symmetry, then you do have two classes, 1 and E. Otherwise, you don't have one class. Okay, so this is this reason. And actually from here, actually that part I'm going not, I plan to talk about, but sorry, I don't have time. That is from here you can see that anomalous rate diffusion category cannot be realized by the model without symmetry, but it can be realized by the model with symmetry. Means anomaly and symmetry almost like same thing. You know, if no anomaly, then no symmetry. When you have anomaly, then you have symmetry. So this is a quite an amazing connection. And then also connect, you can even say that that's a main theme. Or just say that anomaly means symmetry, no anomaly means no symmetry, but anomaly is a bulk. You know, when you have anomaly means you have a non-trivial bulk. No anomaly means you have a trivial bulk. So suddenly you see that with a no anomaly, no symmetry, trivial bulk. With anomaly, with a symmetry, non-trivial bulk. Well, bulk topological order is a symmetry. So that's also see the connection here. And actually later I'll describe this picture from other angle, but this is a main theme of a categorical symmetry or this holographic view of the symmetry. It's really like a symmetry, anomaly, and the bulk topological order are very, very close related. Almost they are the same thing. Yeah. That's from here you can see this. So question, yeah.
Is this anomaly is the diagonal anomaly in mapping class group in the yesterday or?
No. But I will talk about that maybe tomorrow. Yeah. So this anomaly and the mapping class group ST matrix have very close relation. That is a more quantitative description anomaly. You know, at the moment we describe anomaly, it's just a little more handling abstract. So we have anomaly, no anomaly. But what is the quantitative description of anomaly? Then this ST matrix and those kind of things would come into play. Yeah, because you can even say here, because we start to have a quantitative description of topological order. This quantitative description of topological order actually is a quantitative description of anomaly, and also quantitative description of symmetry. So they all come together. Okay, then in some other case, like we have a model with a 1 S is Samian. The quantity dimension is 1, they are bosonic, or they are abelian. Samian have a self topologically a quarter. The self statistic also the I. And this one, Samian can detect self. You know, we have Samian, another Samian go around it, you see a face. So this one is anomaly free. And another one have 1 and 5, and this is called Fibonacci topological order. And the quantity dimension is kind of a golden ratio, so it's a non-abelian. And then we have this a double Fibonacci, which is 2 of these together. This one is realizable. This one have a commuting projector realization. This model have a non-zero central charge, so we believe have non-commuting projector realization, but how? Yeah. And this one, the third one is a Topological model. It's all Z2 gauge theory. Yeah. So we have some example. And then we'll also discuss this S3 gauge theory. Yeah, S3 gauge theory have this data. So this one is a trivial excitation, have a quantum dimension 1 and topological spin 0. This A1, remember S3 gauge theory have a particles. The particles are labeled by the representation of S3 group. S3 group have two representation, two non-trivial one. A one-dimensional non-trivial one and another is a two-dimensional non-trivial one. So this A1, A2 is a gauge charge in the one-dimensional representation for A1. A2 is a gauge charge for the two-dimensional representation of this S3 gauge theory. And so because two-dimensional representation, so therefore the quantum dimension is 2. It's very, very nice. Yeah. But then we have a B. B is a flux because S3 gauge theory have this gauge flux. In two-dimensional space, flux actually is also particle. So B is another particle describing S3 flux. C is another flux, you know. And the flux are labeled by conjugated class. S3 have a two non-trivial conjugated class. So there are two kinds of flux. And we have other things, which is bound state of a charge and a flux. Okay. So total, we have a type of a topological excitation in S3 gauge theory. And so here we list their dimension and topological spin, quantum dimension, topological spin. And this NIJK describing the fusion rule. Yeah, this fusion rule is the NIJK describing the fusion rule. Okay. So this will give you some example, and this one also anomaly free. Give some example of this. Okay. Then whether MTC classify two-dimensional topology, because we say that every MTC is realizable. So then it looks like it's a complete theory for excitation. If you know everything about the excitation, know everything about the defect, then we should know bulk topology order. So we should say it's classified two-dimensional bosonic topology order. Still answer is no. But however, it's classified something like the two-dimensional bosonic topology up to invertible topology order. So there's an invertible topology order which cannot be seen by MTC. So what happens really following? The invertible topology order is a very special topology order which don't have a non-trivial bulk excitation. All the bulk excitation are trivial. They say if excitation trivial, they should be trivial. Well, it have a non-trivial boundary. So you can see that's the thing we missed here. Yeah, we only consider point defect. Considering point defect only is not enough to do two-dimensional, to see two-dimensional topology order. This co-dimensional one boundary also carry some information, not too much, a little bit information. So that was missing by MTC. So the invertible topology order is the following thing. You know, we have a topology order, we have this, the topology order form abelian group. Well, it's not really group, so we call it abelian commutative monoid, means there's a multiplication rule. So the multiplication of two topology order is just a stacking. Yeah, one system, another system stacking together give a third system, just a stacking. So this is the multiplication of two topology order rule give you this defined monoid. The reason is monoid because sometimes we can have a topology order A. We cannot find any other topology order such that the stacking gives us a trivial topology order. Means no inverse. So for the Fermion system, the famous invertible topology order is for Fermionic one is integer quantum Hall states. And for fractional quantum Hall states, they are all non-invertible. And also for bosonic two-dimensional topology order, the invertible is the E8 quantum Hall states. Yeah, it's just a name, so I won't go into the detail here. And so actually, the invertible topology order have a classification. In 2+1 dimension, we have a Z class, just the stacking of E8 quantum Hall state. For Fermionic one, is a P plus IP superconductor stacking results give us a Z class of a Fermionic topology order, etc. In 3+1 dimension, we believe there's no invertible topological order. Maybe not proof. But in fourth topological dimension, there's a Z2 class and etc. So we have this story. Yes.
So consistent pentagon identity of F symbol does not see invertible topological basis.
No, this modular tensor category do not see invertible one at all. Invertible topological have no onion. The reason is following. When you have onions, onion cannot hop between layers. So if I have two layers of topology, each one have onion. Onion as a topologic station, they cannot be destroyed by themselves. So onion cannot hop from one layer to another layer. And so therefore, when you have a non-trivial onion, so stacking layers, you always get more onion. You never get less onion. So that's why this the stacking operation is not group operation. It's about the monoid operation. But however, if some topology have no onions, then stacking them still have no onion. So they form a group. They have an inverse. Okay, so that's one thing. Another thing is that why we have a fraction order in 3 dimension, not in 2 dimension, really because in 3 dimension, the layer, 2-dimensional layer can have non-trivial, non-invertible topology order. Stacking non-invertible topology order gave us a layered structure which cannot be destroyed. And so therefore this foliation would persist. And so that's a fraction order is intrinsically related to this non-invertible topology in 2 dimension. In 2-dimensional space, we can stack 1-dimensional chain. But we don't have a non-trivial, non-invertible topology order as a 1-dimensional chain. Then we don't have a fraction phase in 2-dimensional space. So existence of a non-invertible topology order in 2-dimensional space tell us we can have fraction phase in 1 higher dimension or 2 higher dimension, because this is stacking non-invertibility. When you're stacking more and more layers, it became more and more complicated. So this kind of UV structure cannot be renormalized away, no matter what you do. So there's a UVR mixing. Yeah, this is very much related to this fraction order. Yes.
Are there lattice realizations of the? Well, the 1+1D one, the fermion, that's just a type chain, but
all these have lattice realization.
Right. Okay, even the E8 phase.
E8 type, but it's not soluble.
Okay.
It's belong to that non-soluble.
Okay.
And this one have a soluble, exact soluble model to realize on lattice. Yeah, there's recent paper, lattice realization, Hamiltonian lattice realization of this model.
Is it just kind of accidental, or is there like a dimensional reason why, like in 2+1D they're not?
Yeah, it is. Okay, maybe in 2D, if you go one, the Z class means we have a Pontryagin class in 1 higher dimension. So Z class all relate to this gravitational Chern-Simons term. The Z plus Z in 6+1 means that in 8 dimension, there's 2 different Pontryagin class, the P and the P2 and the P1 square, something like that. Yeah. So I have 2. And here it's just P1, we have 1. And in other dimension, we don't have Z class because we don't have a Pontryagin class in 1 higher dimension.
Okay.
But here, Z2, we have some so-called Stephen-Winnig class. All this algebraic topology come in. So it's a lot of fun, also very scary.
So is it that's Stephen-Winnig class in 1 higher dimension, that's realizable by a commuting projector?
By commuting projector, yes.
But the Pontryagin classes are not.
Cannot.
Okay,
Yeah.
interesting.
Yeah, that's a thing. But you can say P+IP is soluble, but soluble in terms of free fermion, not in terms of commuting terms. There's less of solubility,
Is it simply because the fermions don't commute?
No, not because of that, or because of definition of solubility, because in the free fermion, it's still algebraic complexity. And we say that one is soluble. When you have a commuting projector, it's order 1 complexity.
Okay.
It's not, we don't even need to put the computer to diagonalize the algebraic large matrix. The many body is exponentially complexity. We have diagonalize exponential large matrix to solve it. And in physics, we usually say this algebraic complexity means soluble for free fermion theory. Okay, and so maybe let me just try to finish it. And so there's other things, but I don't want to go through this. So and here I just want to say that so far we have modular tensor category theory described by N, F, and R. This kind of data. At the beginning when we do this topological quantity inertia, we have ST matrix representation of a modular group to describe topological order. So now we have two way of describe topology, one through puncture, another through ground states. And when we combine these two descriptions, there's a lot of relations, like this Valenda formula, this S matrix and the fusion ring are related by this amazing formula. Okay, and also this topological spin and the T matrix are related by this formula, a very simple formula. So there's a lot of relation. Then, because there's a lot of relation, and also we have a lot of consistent condition for this N and R, F and R. There's a lot of condition, and those conditions can be translated into condition on S matrix and the T matrix. So this way, using modular tensor category theory, we obtain a lot of additional condition we don't know before on the ST matrix. So this is you can say I'm too ambitious. Okay, so you can see for the ST matrix, we used to have a condition that is yeah. Interesting. Okay. Yeah, okay. Yeah, this is okay, let me do this, explain what I'm doing here. Okay, from here, we can express Nijk using S matrix. And then if you know S matrix, we know Nijk. If you know the Nijk and the spin, we know S matrix. So it's in both directions. So therefore, originally I'm thinking, yeah, we should formulate a theory using ST matrix to write down a theory for topological order. But equally well, because these two set data can give rise to each other as one-to-one. So we can also equivalently using Nijk and the topological spin using this pair of data to describe topological order. So I will formulate our condition on ST matrix, but not directly, but on Nijk and Si. And so this is what I try to list here, and yeah, Nijk would satisfy this some condition here, and there's some other condition. And then there's amazing thing that this topological spin on Nijk also satisfy this condition where this V is this complete combination of Nijk. So there's a lot of study, and we get a lot of condition, and so then we can use Nijk to construct ST matrix, and then ST matrix should form a SL2 representation, and etc. Basically there's a lot of math. It's a very messy, but the computer don't mind messy things as long as deal with the numbers. Then you can put all this into the computer. Then finally you get this table for a modular tensor category. But this table there's some it's not very rigorous in the sense we only classify ST matrix. The ST matrix and the modular tensor category is not one-to-one. There's a little bit of missing things, and but if you don't mind this missing thing, then you get some table. And so there's like this Samyang theory are described as a Laughlin wave function. And there's so the one with the red, we know some kind of wave function realization, So from here we get some kind of quantitative theory of a topological order. Yeah, I think I will take a break here, a 5 minutes break here.
I think we will meet 10:20, 5 minutes break. Yeah. Thank you.
1120.
Sorry, 1120.
Yes. Yeah. In the CFT, there is a fusion category, and but in a different way. A CFT have this so-called topological line. Yeah, the topological line actually their fusion form fusion category, and so actually this I'm going to discuss maybe next. That is this topological line is a symmetry, and their fusion category became symmetry, and they're all connected. Yeah, so actually this really is a point of view that the fusion category or module tensor category, so CFT contains hidden module tensor category because the topological line actually gave rise to module tensor category, and then we hope maybe this hidden module tensor category in the CFT completely describe the CFT. So that's a way to describe CFT from this symmetry point of view. Okay, maybe let's start. So after all this discussion about topological order or category, something more fancy stuff, and so let's go back to this physical question, the phase diagram. You know, in the first lecture, we talked about we are considering a 1+1 dimensional system with S3 symmetry. That seems a very simple situation. We should know everything about it. Why we talk about that? And we know that we have a S3 have a 4 subgroup S3 and Z1 and also Z2, Z3. And in the symmetry breaking phase, there's a 4 symmetry breaking phase, which have unbroken symmetries given by S3, Z2, Z3, and Z1. So we use unbroken symmetry to label those symmetry breaking phase. And because they're discrete symmetry, these are gap states. And so there's already a question that whether this do we have other state in addition to this 4 symmetry breaking state? Do we have other gap phase like SPD phase for S3 symmetry, etc.? According to group cohomology theory, the answer is no. But whether some other theory, you may go beyond group cohomology, you get something, you know. So there's a similar question here. But the most interestingly is that for this 4 symmetry, there's a 5 pair of group subgroup relation. So those are 5 pairs of group subgroup. So we can't expect for every group subgroup relation, maybe there's a continuous phase transition. So maybe we expect to have a 5 continuous phase transition. So we did some numerical calculation. Indeed, we find that there's a 5 transition. Indeed, they all looks continuous. But the one with connecting S3 to Z1 we are not so certain. But it looks continuous, but we are not so certain. Other transition also looks continuous, but we are more certain. The reasons are because we can identify the CFT for the other 4 transition, but at the moment we do not know how to identify CFT for this transition. Yeah, so that is one of a big question. Yeah, so this one is we don't know the CFT, so we are now pure numerics sometimes can be misleading. You know, maybe it's very weak first order, or maybe for some other reason. If you don't know CFT, we are not so certain. Numerical data quality, this one is not as good also. So for this Z2 to Z1 transition, that's a symmetry, Z2 symmetry breaking. So that's the Ising model, C to 1/2 Ising model. And for S3 to Z3, it's also we break Z2 symmetry. And that's also C2.5 of CFT, but maybe with some different combination. There's slight difference. I try to say different. The reason I say different is following. This symmetry, you can see the at the critical point of this transition do not have S3 symmetry, but the critical point of this transition have S3 symmetry. So from point of view of S3 quantum spin system, these two critical points, although looks both equal to 1/2, I think transition point, but there's slight difference. This S3 quantum number assignment is different. It's just, and maybe just that. The S3 quantum number assignment can be different. And then we have a similar story for Z3 to Z1 transition is C equal to 4/5 CFT. It's less than 1, so it's a minimum model. It's a 6/5 minimum model. And this one is this one. And we know this because we basically can compute the central charge. This red line is central charge. And then from central charge is we get those values. So because the minimum model we feel pretty certain, and that's it. And there's certainly many other calculations for these two cases. It's well studied. The POS model, IC model is real studied. Because those four situations is so well studied, I would say this one must be known. But unfortunately, I don't know. I tried looking for literature. If someone knows your literature, I really wish whether someone studied this S3 to Z1 transition, or whether there's some result or some theory, some thought about that. However, there's even more because we even have multi-critical points, so we can have multi-critical point here and here. And then when we tune the parameter, then we may have a 4-phase meet at one point. Again, this part is not totally certain because there's maybe a small segment of kinetic transition. Maybe it's a single multi-critical point. It's but I think probably this one is indeed a multi-critical point connecting 4-phase, and those are multi-critical point connecting 3-phase. So then we have a rich issue of what is CFT of those multi-critical points? Yeah, there's so those are questions we want to address. So therefore, what I'm going to do in this lecture and the lecture next Monday is we try to use categorical symmetry approach to obtain or constrain those critical points. And we hope we can determine them completely, but if not, at least we constrain them largely. There are only a few selections. And this is normal because when you have symmetry can constrain the dynamics. And so therefore, if you know the symmetry, then you can constrain the CFT. However, the categorical symmetry is like symmetry, but more than Euro symmetry. So it's a kind of extended version of symmetry. So actually, the categorical symmetry would constrain more, and we get more information. Basically, that is the message I try to bring here. So one thing is that remember I said it's S3 to Z1 transition. We don't know, but the moment I think you can say that there's maybe one of the following 3 cases may be true. One of them must be true. Either this S3 to Z1 transition is described by the same CFT as S3 to Z2 transition, which is this POS model CFT, this one. They'll be strange because symmetry breaking pattern are different, but the CFT is entirely the same. I mean, it's completely the same. Even the assignment of a quantum number is the same. So, yeah, I don't know whether people can rule out this, at more, I feel this may be unlikely, but yeah, very strange result. Or it's described by a CFT with central charge more than 1. This is also surprising because we know there's a unstable. Okay, this CFT is with a large central charge only, but only one relevant operator. We already know a CFT with a 2 relevant operator with a of the same or symmetry. The certain charge is only 5/6. So there's already a CFT with certain charge 5/6 with already with two relevant operator. But however, to describe this transition, that CFT don't work because that's a two relevant operator. To have a stable condition transition, we have to have one relevant operator. Then we require there's a CFT with only one relevant operator, but with a large central charge. I think this one is possible, yeah, but kind of strange. Or maybe this continuous transition just do not exist. Just like the continuous transition between Z3 and Z2 do not exist. This is the Landau forbidden. The Z2 and Z3 is not group subgroup relation. There's no continuous phase transition. So maybe we have same thing, the S3 to Z1, no continuous phase transition for some reason.
So when you consider categorical symmetry for the theory where they already have a symmetry.
Yeah.
So what is the real, the difference?
Yeah, I will explain categorical symmetry in a moment. So right now, I just use the word. I have not explained what is categorical symmetry. Yeah, I will do that. That's the main topic of this of the remaining lecture. Yeah. Okay, so that's one thing. Another thing we want to obtain is that using categorical symmetry is that the transition from S3 to Z1 and transition from Z3 to Z2 are equivalent transition. There's a duality map one to another. Yeah, and this one is it's something not definite result. That is so if S3 to Z1 have a continuous transition, then the Z3 to Z2 must have continuous transition. If you think Z2 Z3 cannot have continuous transition with a one relevant operator, then S3 to Z1 cannot have a continuous transition with a one relevant operator. They're really completed duality mapping between two. And this can be seen from this categorical symmetry. And also the CFT describing the two transition, if that continuous, the CFT describing two transition have the same CFT. Maybe the naming operator can switch, but the scaling dimension, the spectrum scaling dimension are all the same. Central charge is the same. So yeah.
If I remember correctly, you said previously that for these possible phase transitions, it looked like the central charge was 1.3.
Yes.
So is it? Can you show that it can't just be a direct product of these two minimal models?
Yes. Maybe yes. Yeah, that we haven't tried to say that. The concern is that whether there's a more than one relevant operator or not. Yeah, because this is stable transition, so it must be CFT with only one S3 symmetric relevant operator. When you do this direct product, maybe there's more than one relevant. There's concern.
Both of these are stable.
What? Because there's a line, you can see this transition is a whole line is continuous. So maybe the single CFT describing this whole line for continuous transition. Just like here, this is Ising model describing whole line for continuous transition. Yeah, so that means there's only one relevant direction here, only one relevant direction. Yeah, so this is I wish some people that are expert in this they kind of give some stuff. I'm very surprised that even for this very simple thing in one dimension, we still have open question. We should know everything here, but this only the first simplest non-abelian group. I can imagine I pick any non-abelian group and try to construct the global phase diagram. We may see a lot of phase transition, a lot of critical line, and we don't know their CFT. So actually, even in this 1D system with discrete symmetry, maybe there's still a lot of unknown, and we need some machinery, a systematic machinery to really, get those information. Now we should know everything, for 1D, but certainly that's maybe we need new machinery. That's what I'm hoping. Then this new machinery maybe may apply to higher dimensions, so maybe get a more systematic understanding of a CFT. Actually, that's the main motivation for those study. Yeah.
Very nice physical question. So when you have this phase transition,
Yes.
when you approach this boundary of phase transition, in traditional sense, the system develop some long range correlation
Yes.
even in this
yes.
case?
Yeah, indeed. There's other parameter. All those transitions, those symmetry breaking transition.
You can
There's a
define.
local order parameter. The Kinston-Long theory works, but also do not work because Kinston-Long theory at the mean field level predict that this transition, predict this transition like Z3 to Z1 is the first order because it have cubic term. Kinston-Long theory can have first order transition, but in reality, quantum theory, this transition is the second order. It's continuous. But the transition is really described by other parameter. Yeah.
But this is just one-dimensional system.
Yes.
Then just by looking at the divergence of correlation lengths, can you discriminate different phase transition?
Yeah, you can. Yeah.
Oh.
So
how? What's the character?
Oh, there's a scaling dimension. You know, when have operator near critical point, they have algebraic correlation, and there's scaling dimension.
I see.
And so this exponent. Actually, I didn't show the data. You know, in this tangent network computation, the exponent can be computed.
I see.
And but not for which operator we can compute the spectrum of a lot of the exponent. You know, so there's a 1/2 or maybe the 1/16. You know, those exponents there.
I see.
And then when you actually measure this spin correlation function at the critical point, you will see this algebraic decay with that exponent.
Right. I see.
Yeah.
Okay.
So this so when I say CFT, I really mean this collection of those exponent. You know, it's or no. But we wish we know that for this transition. For this transition, we don't know. Numerically can compute that, but theoretically, we don't have a theory to predict what kind of exponent you expect to see. For other full transition, we know. We know there's CFT. Knowing CFT means we know all the exponents, actually. Okay. So now, what is categorical symmetry? But let me say why we have a categorical. Why we do this? Because we know the symmetry can constrain the dynamics. Different symmetry give you different constraint of dynamics. Similarly, this anomalous symmetry can constrain dynamics. Higher symmetry, anomalous higher symmetry, algebraic higher symmetry, anomaly, they all constrain dynamics. So therefore, from this sense, all those symmetries are similar. They just constrain the dynamics. Then the categorical symmetry is just a unified way to decide all this in the same formalism. So all those constraining dynamics can be viewed from this point of view. Okay, it's just unifying all those symmetry in the one framework, in a single framework. Then what is categorical symmetry? You know, I already mentioned a little bit. The symmetry and anomaly are related. So actually, categorical symmetry is a gravitational anomaly, but actually should be mostly it's a non-invertible gravitational anomaly. And it's a symmetry plus dual symmetry. You know, basically, you know, when we have critical theory, we know there's order operator, disorder operator. If you order disorder operator together at the same footing, then that's some flair of a categorical symmetry. Viewing these two together at the same footing, that's another point of view for categorical symmetry. Because gravitational anomaly is a question of topological in one higher dimension, so categorical symmetry actually is a topological in one higher dimension. And so actually, I'm going to use this mostly. And topological in one higher dimension actually is a braid diffusion non-degenerate braid diffusion category or MTC. So this is also the same thing. And it's also equivalent class of algebra of a local symmetric operator. So I will mostly presenting this point of view and this point of view, and also this topological in high dimension, this point of view. So there's many different ways to look at categorical symmetry. But however, I just want to say that many people, maybe most people, use categorical symmetry to mean this algebraic higher symmetry or non-invertible symmetry. And in this lecture, we don't use that meaning. Non-invertible symmetry is non-invertible symmetry. Categorical symmetry is something different. It's in one higher dimension. Even dimension is different. So let's present the point of view. The categorical symmetry is a symmetry plus dual symmetry, or the order parameter plus disorder operator. So it's that point of view. So that point is the easiest actually. And so let's again consider example like the one-dimensional transverse field Ising model. That's a Z coupling and X coupling. Okay. The Z2 symmetry is just a spin flip, the spin up, spin down flip. That's the Z2 symmetry. Okay. So what is a symmetry? Oh, you say, oh, it's this. But here I want to say that let's not look at symmetry from transformation point of view. Okay. Let's look at the symmetry from excitation point of view. The reason is following. When you're looking at symmetry from transformation point of view, you actually break the symmetry. Means you have an instrument whose interaction with your system breaks the symmetry. Then you examine the transformation property of the symmetry. But however, if you have a symmetry, if your instrument and their interaction with your system do not break symmetry, there's an issue. How do you measure symmetry? If you do not break symmetry at all, then you cannot perform transformation. So that point of view is related to this. Now we're using excitation. So suppose let's assume we think this consider this left-right basis. Okay. Then our vacuum, let's assume vacuum is all the spin point to the right. Then the spin point to the, this is right. The spin point to the left, this red one, we call some charge. Then because this Z term, the Z term flip this left or right. So this two Z term. So that means these two, because we only have these two Z term. So that means we can only annihilate a pair of left spin, not a single one. And so therefore we have mode 2 conservation. Only a pair of spin can annihilate to a pair of a charge can annihilate, a single charge cannot annihilate. So that's this using fusion rule to describe Z2 symmetry. And just conservation law. Conservation law gave us Z2 symmetry. Then we can also choose in the up and down basis, like this up and down basis. Then in up and down basis we have domain walls. Then we use domain wall as something. Then we suddenly realize that domain wall also have a Z2 mode 2 conservation. The single domain wall cannot disappear by itself. The two domain wall can disappear. So it's very similar to, it's very similar to this left spin. There's a Z2 conservation for left spin, and there's a Z2 conservation of a domain wall, up and down domain wall. And that's it. So this is Z2 mode 2 conservation is a Z2 symmetry, that's the ordinary one. And for domain wall Z2, mode Z2 conservation is a Z2 dual symmetry. We call that dual symmetry. And then for people who are familiar with all the disorder operator, this domain wall is like a disorder operator, something along that direction. So that's what I say. So you can see that this simple Ising model have a hidden symmetry, have a Z2 symmetry and a Z2 dual symmetry, have both actually. Actually, one imply another. If you break one, you also break the other. But if one appear, another also appear. But at least formally we can have this. Then so therefore the combination of these two symmetries, Z2 and Z2 dual, is a categorical symmetry. So that's what they mean by categorical symmetry. And we use this very simple, this string symbol V, not the times. When we combine two symmetry, it's just Z2 times Z2. Well, why we do V, not times? And so let's consider, to understand that, let's consider this symmetry more carefully. When you have a symmetry, we should have a charge operator. the operator create a charge. But here we want to consider operator create a pair of charge. Because the operator creating pair of charge representing the mode 2 conservation, I mean, 2 charge can annihilate. So therefore, we have the operator creating pair of charge is allowed operator. Okay. So to create a pair of Z2 charge, we just have a Zi, Zj. So this operator create a pair of Z2 charge. Then the operator which create a pair of dual symmetry charge is actually a string operator. So it's a multiplication of x, so the sigma x between I and j. It's a segment. It's a string operator. And that's a flip a spin in a region, and then that's a domain 1. That's create a 2-domain 1. So this string operator always create a 2-domain. Okay. And so this seems it's kind of strange because to creating 2 charge, we should have a 2 local operator. But for the dual spin, it's not 2 local operator, just it's a string operator. But here, let's say maybe this is a generic case. In general, we need a string operator to create a 2 charge. Then we also view this as string operator. This is just a string operator with empty bulk. The bulk is identity. So it's also so actually that's a terminology we can use. We view both as a string operator. And so this pair of charge are created by string operator, and the charge are located at the boundary of the string operator. Some kind of strange way to think of this. But anyway, so but when you have this charge pair operator, then something interesting happens. We can study more. We find these 2 different charge pair creation operator have non-trivial commutation relation. If the boundary kind of straddled in a non-trivial way. If the boundary is not I don't know if the boundary linked is non-trivial. If the boundary is not linked like this way, then they commute. And but however, we can view the different order of applying operator as time direction. So this 2 different order doing multiplication this vertical is time direction. Then these 2 pictures, the comparison of these 2 pictures is almost like this, because this end can annihilate, then we get a loop going around the charge. That's like a braiding. Yeah. So indeed, even though in 1-dimensional system, but the operator algebra of this string operator contain braiding. And so at that point, that's we view the string operator, the boundary as our particles, but from the string operator, somehow we can decide the braiding statistics of this particle, even though this one is 1-dimensional. So somehow the different order of applying operator gave rise to another dimension, and we suddenly get a braided diffusion category, even for this 1-dimensional thing. Yeah. And this is exactly what we want. Yes.
So can we consider this string as a topological object in space-time?
Yes.
So
I think yes. Because this operator, this string operator, we apply that in the time slice.
Yeah.
Yeah, we do Hamiltonian, but you can rotate the 2 directions. It's really become
I see.
Yeah.
So that is the part of the categorical symmetry.
yeah, exactly.
function?
Yeah. So indeed, this closely related to this what's the topological line defect of domain, topological boundary, topological domain wall or something. I don't know what's the official name. But line defect only 1 dimension. In any dimension, what do you call that? Topological membrane, topological brane. Yeah, maybe topological brane probably is the favorite name. Yeah. And so because of this non-trivial commutation relation for the charge pair operator, so we say that's a V. That's what this V means. They are not independent. Usually when I have Z2 cross Z2, the charge pair creation operator do not have this non-trivial braiding. And let's call this a braiding. Yeah. And so yeah, that is the key. Now you can see that this way of looking at the symmetry, we not only have symmetry, have a charge, but also somehow there's a braiding. And so this kind of structure start to appear, and this will play a key role. Okay. So let's look at this operator carefully. Actually, it's already clear that so this dual Z2 charge operator, this operator creates a dual Z2 charge. If you look at it, it's actually a symmetry transformation operator, but only on the patch, on the segment, not everywhere. And this is important because usually when you do symmetry transformation, we do global transformation, we do symmetry transformation everywhere, but we don't need to. We just say we only need to define our symmetry transformation on the patch. That's enough because our Hamiltonian is a sum of local operator. Then this patch operator, patch symmetry transformation is enough to determine which local operator is allowed or not allowed. We just commute this patch symmetry operator with another local operator. If they commute, then we say this are allowed. As long as this local operator is not close to the boundary, we have this condition that's far away from boundary. So therefore, this patch symmetry operator is enough to determine the symmetric local operator and determine symmetric Hamiltonian. And maybe this is useful because to define operator acting on infinity system is sometimes troublesome. And but now we say that even when your system is infinity, you can define your symmetry transformation in a finite subsystem. And that's enough to build everything. So this kind of thinking is very helpful actually. So it's really a little symmetry transformation. And so then from the similarity, we will say, well, maybe this Z2 charge pair operator ZI-ZJ should generate a Z2 tilde transformation, dual symmetry transformation on the middle, on the patch. But here you don't. The box is empty. They don't do anything. Okay. Then actually, we can make them to do something by doing this Kramer's linear duality transformation. When you do this transformation, that is we have another model. The spin now live on a link, not on the side. And then we have this mapping. The X go to this dual spin has a mapping like that. Then when you do the mapping, you'll find this the Z2 charge pair operator became actually this should dual spin actually a tilt here. Yeah, this is dual spin. Became the one with non-empty bulk. And so this one indeed is a Z2 dual symmetry in the dual model. Yeah. So indeed we have this really very equal footing symmetry. Yeah. And also the original this string operator which is doing Z2 symmetry transformation became a pair of empty bulk operator in the dual model, which only created two Z2 charge, Z2 dual Z2 charge. So this so from here you can see that this putting two things together is kind of more symmetric way to look at this I think model. And so this is kind of from operator algebra point of view to look at those categorical symmetry. And actually this operator algebra point of view have a holographic picture. This 2v2 symmetry became explicit and obvious when you have doing this holographic picture. It's very similar to ADF CFT picture where global symmetry in the boundary became gauge theory in the bulk. Here is the same thing. If you have Z2 symmetry on the boundary, we have Z2 gauge theory in the bulk, and it works. Okay. When you have Z2 gauge theory in the bulk, which is 2 plus 1 dimensional bulk, And we have a trivial extension that's nothing. And we have a little charge we call the E. And we have little flux we call M. The both are boson. And we also have a little charge flux bound state, which is fermion. Okay. It turns out that this the Z2 charge can be viewed as the dual Z2 flux. And Z2 flux can be viewed as a dual Z2 charge. Because the domain wall in the Z2 is like is the flux of Z2, but the domain wall is a dual Z2 charge. Yeah. So that's how we have this relation. Okay. And so therefore you can see in one higher dimension theory, both E and M have a Z2 fusion. They have a mono-2 conservation. So we immediately have this Z2. We have two symmetry immediately, and explicitly we have two symmetry. And also this E and M, although they are both boson, they indeed have non-trivial mutual statistics. So that's also in line with from our operator point of view. Yeah, it's they all fit. Yeah. So therefore, it's therefore this Z2 gate theory in one higher dimension is also, we can also call that a categorical symmetry. It's a same, give rise to same picture of this string operator picture. Okay, so now let's so basically this the conclusion is that this categorical symmetry can also be viewed as a topological order in one higher dimension. Yeah. So now let's consider a situation where this E particle condense. Okay. So E particle can condense in the Z2 gate theory. And that's what is that? That's Higgs mechanism. You know, E particle like a charged field, bosonic charged field, they condense. You Higgs. That's a Higgs. You get a Higgs phase. Okay. And in the Higgs phase, this bosonic field have non-trivial, non-zero exclusion value. In this case, the M and F was confined because E and MF have non-trivial mutual statistics. So therefore, when you have M and F, the MF will create a branch cut in this condensate order parameter field. And this branch cut is long, so you have this have energy along the branch cut. So you have so energy diverge, linearly diverge, and so therefore this MF have a linear confinement in this condensed space. And also the E condensed phase, the E particle is trivial because it can be absorbed by the condensation. So therefore, in the E condensed phase, there's no excitation. So therefore, this I expected this trivial topological order is a product state. Okay, it's really product state. And if you consider the domain wall between the Z gauge theory and this E condensed states, the E condensed state is a product state, it's trivial, it's a vacuum, we can remove it. So this domain wall can also be viewed as the boundary of a Z2 gauge theory. Yeah, and this part is standard, but that's the main point. The boundary of Z2 gauge theory can be viewed from condensation point of view, because the condensation give you a trivial phase in other half. Remove trivial phase, then you say the condensation can induce a boundary. So that's really the picture here. So therefore, you can see that the M can condense. If M condense, one always condense. You know, one is nothing, so one always condense. So that if we have a boundary where the M1 condense, M condense also give rise to the trivial phase. And so therefore, so there's a one boundary is M condense. It's a gapped boundary given by the M condense. Okay. And in this phase, M condense. So therefore, the Z2 dual Z2 symmetry is spontaneously broken. But the Z2 symmetry is not broken, but E do not condense. So therefore, this pattern for condensation gave rise to the Z2 symmetric phase, but the dual Z2 spontaneously breaking. That's one of the gapped boundary. And this corresponds to the gapped phase in the Ising model. Z2 symmetry not broken is a normal state, not symmetry breaking state. Then if there's another boundary induced by the E condensation and one condensation, and then in this case, the Z2 symmetry is spontaneously broken. but Z2 is not broken. So it's really this picture. Usually we consider Z2 symmetry. There are two phases of Ising model. One is Z2 symmetric, another Z2 symmetry breaking. But we can also include dual symmetry. This Z2 symmetric phase corresponds to Z2 dual spontaneous breaking. Z2 spontaneous breaking phase corresponds to Z2 dual symmetric phase. So really in line with this picture. So this is a kind of a strange way to understand the symmetry breaking and the symmetric phase, but using categorical symmetry point of view, from that point of view, or from Bock point of view. And the message is that the boundary is given by the condensation. So different pattern of condensation give rise to different boundary. And this suddenly became very, very important. Categorical symmetry is a Bock topological order. It's a symmetry. And this symmetry determines what kind of condensation is possible and determine what kind of a phase is possible controlled by this symmetry. Yeah, and this is the main message, yes.
So at the critical point, the Ising CFT, I think usually people say it's topological defect lines. Again, it's an Ising MTC category, right? But where like the Kramers-Vannier duality is included as some kind of, categorical symmetry.
Yes.
But that's different from.
Just a moment. Let me comment that just a moment. So now you can see, what happened at the critical point. Critical point touch this Z2 symmetric phase. So the critical point should have Z2 symmetry. Because it's a limit of Z2 symmetric phase, it should have a Z2 symmetry. This critical point also touch the Z2 dual symmetric phase, dual Z2 symmetric phase. So we also think, this can also have this symmetry. So critical point have both. Actually, that's another way to say that in the critical point, M and E do not condense. So only one condense. So that is another condensation pattern. Nothing condensed is one possible condensation. Yeah. And they have full categorical symmetry. Yeah. And this full categorical symmetry actually is gapless. Is the one with the full categorical symmetry gapless. It's representing the critical point. Yeah. So that is the picture. However, there's one thing, as you mentioned, maybe the critical point, here we claim that this critical point have this kind of categorical symmetry described by the Z2 gate theory. And this categorical symmetry include this Z2 symmetry, Z2 dual symmetry, but obviously did not include the EM exchange symmetry. This Z2 gate theory have an automorphism. When you exchange Z and M, everything is the same. And then you can even say, so actually there's no EM exchange symmetry in here and here, but at the critical point, there's an emergent EM exchange symmetry, and which this emergent symmetry is not included here. So it's against the philosophy, I mentioned maybe a few days ago. We want to include all the emergent symmetry. Maybe that is give us a full information of a critical point. And here we have an example which we did not include EM exchange. But this example is very simple. We should do that, and we do that. If you do that, then the symmetry is enlarged. The topological order in the Bock also enlarged, getting another topological order describing, including EM exchange symmetry. And that topological order is double Ising topological order. So therefore, if you include the EM exchange symmetry, the Ising model critical point is a full, or we call the maximum categorical symmetry is a double Ising topological order. And that probably is a better description. But however, without using full categorical symmetry, this Z2 gate series already give us a lot of information. Yeah, but you can see all these features. I think I would stop here, and so we can we'll continue next week, next Monday. Yeah.
Thank you very much. So now the talk is open for questions. Please ask anything.
So is there any possibility that the critical point, both are condensing? Well,
Oh yeah, that's the thing. So this is answer, so I can continue. So the symmetry, and it's kind of strange, is that this is symmetry, dual symmetry, because they have non-trivial mutual statistics. We cannot break them together. It's impossible to break them together. But we can break one of them. Like if you break, so to break them together is impossible. If you break one of them, then we can get gapless. If we do not break any of them, then this phase must be gapless. It's again associated with a non-trivial mutual statistics. These non-trivial mutual statistics actually have some connection, a flavor of anomalies. So you're having this categorical symmetry enforcing gaplessness condition. It's almost like anomalous symmetry enforcing gapless condition. It's the same flavor, yeah. But this one is more systematic, yeah. And actually, later we'll show indeed this if a categorical symmetry is not broken, the boundary must be gapless.
Yeah. So in when people talk about topological defect lines and 1+1D CFTs,
yeah,
they say it's as far as I know that they only form a fusion category.
Yeah,
because they don't have braiding and
yeah,
more. So in some sense, it's like less structured, but then again, it's also like kind of less restrictive because you can also have non-commutative fusion rules. And in some cases, apparently.
Okay. Yeah, that's interesting. Non-commutative fusion rule, I don't know. Yeah. So since you mentioned this, so let me put this way. So the correspondence is the following. You can see here we have a two-set operator. This W and W tilde. So we consider algebra for both W and W tilde. If you only consider algebra for one, or say only W, then you get an algebra for Z2 symmetry. And then that's a fusion category, right? And so in this sense, the fusion category have this, you can define braiding, they always trivial braiding, so we probably don't mention that, yeah. And but however, when you consider both of this, then there's a non-trivial braiding. What I try to say is that in a non-invertible symmetry, especially when you consider so-called anomaly-free non-invertible symmetry, you really consider this topological defect line and their fusion. But anomaly-free means that we kind of assume their boundary always boils down always a trivial mutual statistics.
Okay.
So a set of a charge operator, which boundary is boils down with the trivial mutual statistics. This set of charge operator would generate some kind of anomaly-free symmetry. And this kind of charge operator can have the fusion can be complicated, can be non-invertible and etc. Yeah. But what you said is something I don't know. That is, in one dimension, the fusion can be non-commutative. And then this non-commutative fusion do not have a two-dimensional analog because braided fusion category require commutative fusion. Then in that case, I don't know. Yeah,
I'm not sure if there are actually like realizations of those.
Yeah, but that's interesting stuff. In the fusion category, we do allow this NIJK where IJ, is the NIJK, IJ cannot switch, it's not symmetric. And that one don't have a braid fusion category analog.
Right.
And yeah, Yeah, I don't know. I don't know the answer. So whether that is
Yeah.
possible or something. Yeah.
But for like, say like the Ising CFT with like the Ising category as its fusion category symmetry, then like this version is saying basically you take the double version and that's the
Yeah, I don't know.
category.
What I'm trying to say is that yeah, okay, yeah. What I'm trying to say is that asynchronous point have a lot of topological defect line.
Right.
If you include all of them, you get double Ising.
Yeah.
Model. Yeah. You get double Ising topology order.
Yeah.
And here when you do this Z2 top gauge theory, we do not include this EM exchange topology defect line. But we consider other symmetry twist topology defect line. Then we get this picture, the small standard picture. But the point is that for every conformal field theory, we should include all the topology defect line, and that gives you maximal categorical symmetry.
Yeah.
And the question is that whether that can be used to fully characterize the CFT. And so actually, I think there's a program to say the CFT is characterized or classified by modular tensor category. So what I'm describing is along that line. That is the full topology defect line is a modular tensor category. Hopefully that can fully characterize the CFT.
Yeah. Okay, thanks.
More question? I have a very naive question. So to my understanding, starting with your some Hamiltonian, you define the topological object, then you find some symmetry obeyed by this topological object. Then you classify this symmetry breaking.
Yes.
So my question is, can you capture the final this physics starting with just original Hamiltonian applying standard Ginzburg-Landau symmetry breaking?
Yeah. So
it's possible.
Yeah, it's possible. Let me
then why do you need all this complicated category?
I have a slide for this. Let me see. Yeah, it's here. Yeah. So let's try to label gap and gapless states. And so we know that for the Ising model, we consider Z2 symmetry. There's a Z2 symmetric state, which is the gap. That's ordinary paramagnetic state.
Right.
And there are also Z2 symmetric states, which is the gapless at critical point. That's also Z2 symmetric.
Yeah.
And we have Z2 symmetry breaking state, which is the gap. So you can see in this way we label things. The both gapped state and the critical state have Z2 symmetric. So there's a label of degenerate. Okay. But however, if you using categorical symmetry, then we have this gap is Z2 symmetric, Z2 tilt breaking. But the critical state actually is both symmetric.
Right.
And that one is a Z2 breaking and Z2 tilt symmetric.
Right.
So basically, in this
one-to-one correspondence.
Yeah, there's one. But however, in the new label, we break degeneracy. So these two states are different. So this really means that we even view the gapless states and gap state at equal footing via condensation. And so they all just different pattern of condensation, which led to different symmetry breaking pattern. So this kind of symmetry breaking pattern and condensation, including gapless states now. If you only do this, if you ignore the gap states, these two symmetry breaking and breaking, that's good. They label two states. We include the gapless states, they're degeneracy. So that means using Z2 symmetry picture, we cannot distinguish two different situations. And then the categorical symmetry give you more detailed information. You can distinguish that. But once you can distinguish that, it have meaning because you can compute the physical property from your label. Now you can see that these three phases have different label. And from this label, we can compute their physical property. Like, yeah.
So there is some analogy to two-dimensional Kostalis-Saulus phase transition. This is ordinary spin system,
Yeah.
but they introduce vortex, anti-vortex, and they
Yeah. Oh, yeah, yeah.
describe the critical phenomena of this topological object.
Exactly.
But,
Exactly.
but you can still understand from ordinary spin degree of freedom.
Yes.
Yeah.
The philosophy is similar. That is, you can see, we can understand that this, if you're approaching critical point from the symmetric side,
Mhm.
this critical point is obtained by the condensation or proliferation of this Z2 charge.
Right.
If you're approaching critical point from symmetry breaking side,
Mhm.
is a proliferation of a domain wall. That's the topological defect,
Right.
which drives the transition.
Yeah.
So in that spirit, it's similar.
I see.
But however, the point of view is that because critical point have this 2-point view,
Mhm.
let's bring these 2-point view together.
Mhm.
Then consider everything via condensation. And because in this, you know, you are totally right. In this, like some kind of fancy formalism, you know, what's the use of it?
Mhm.
Because in this formalism, both gapped and gapless states can be viewed as a condensation of some pattern.
Mhm.
So pattern of condensation determine both gapped and gapless states.
Mhm.
Then by studying pattern of condensation, we can derive their property. We can obtain their property. So this is so that's the usefulness of this. So why we go to one higher dimension gets so fancy, but then we'll behind after that there's a unified formalism
Mhm.
to describing all these gapped and gapless space at equal footing.
Okay. Thank you.
Yeah. This.
So I think you explained the duality for bulk 2 plus 1 dimensional Z2 gauge theory. And if the bulk theory is 3 plus 1 dimensional Z2 gauge theory, so what is the category symmetry in the boundary?
Let me see where is it? Yeah. So this is a picture for 2 plus 1 dimensional boundary and a 3 plus 1 dimensional bulk. So you can have a Z2 symmetry in 2 plus 1 dimension. Then the bulk will be Z2 gauge theory. The charge is still particle, but the flux became loop strings. And then the symmetry is still Z2 symmetry is a charge, but dual symmetry is a one symmetry. It's a higher symmetry because of the charge became loops. And so therefore, if a string condense, it give a boundary which are just ordinary Z2 symmetric phase. However, if a charge condense give you another boundary, this boundary have is a symmetric phase for the higher symmetry.
And can you generalize this duality to any higher dimension?
Yeah. So this is this picture, you know, just higher symmetry become that's the reason this higher n-dimensional space. So the Zn symmetry is due to the Zn-1 symmetry. This is kind of higher symmetry. And actually, this picture even works for the non-abelian group. For abelian group, this is Zn 1-dimensional higher symmetry is still a higher symmetry. For non-abelian group, this symmetry is not higher symmetry. The dual of G symmetry is a n-1 symmetry, but not n-1 symmetry. It's when I say n-1 symmetry, I kind of assume there's a higher group describing that, but this one is beyond the higher group. So this one, the one of non-invertible symmetry. Actually, this is the simplest non-invertible symmetry. That's a dual of ordinary non-abelian symmetry. Is a non-invertible symmetry. And their symmetry, the symmetry transformation of this non-invertible symmetry is generated by the Wilson line operator. And the Wilson line operator, the fusion Wilson line operator is not invertible. So that's it. Yeah. So this is simplest non-invertible symmetry.
Thank you very much.
So yeah, I have a few questions. So first of all, when you say the SS3 of categorical symmetry, you mean that you mean the condensation of anion in one higher dimensional theory. Is that right?
Yeah.
Then
Yeah, exactly. We describing when I say condensation gave rise to all this phase, gapless phase. What it really means is a condensation to the boundary. So condensation of anion in one higher dimension, but to the boundary.
okay.
And so basically, the boundary is determined by the anion condensation. The pattern of anion condensation gave rise to different boundary.
I see.
So using that, we try to study different phase in one lower dimension.
So another question is, so in the example of the Z2 gauge theory, in 2+1 dimension, so the non-condensability, or the relation between the condensable anions can be also seen as an anomaly of one-form symmetries, right? Which can be matched by, even one higher dimension. So, is there any relation between?
What's this?
So the Z2 gauge theory,
Yeah.
Has two one-form symmetries.
Yes.
Electric and magnetic, and they are anomalous, right?
Yeah.
And which can be matched as, one higher, even higher dimensional SPT.
Oh, okay. Yeah. Okay.
So is there any relation between this picture and categorical?
Yes. Yeah. Okay. Yeah. I answer yes. Yeah. It's basically here we say the lower dimension system have a zero symmetry, but you can this don't have to be zero symmetry. It can be one symmetry, two symmetry, the same thing. Yeah. And when you have example of a Z2 gauge theory, what is the symmetry of a Z2 gauge theory? It's actually a very tricky question. And I try to say that the Z2 gauge theory have no symmetry. No one form symmetry, no symmetry at all. But that means at the energy scale of all the excitation, Z2 gauge theory have no symmetry. So their bulk is trivial. However, if you assume like a Z2 charge of very high energy, you only have a Z2 flux. Then below the energy gap of Z2 charge, then there's an emergent symmetry. Actually, that'll be one symmetry. Then this emergent symmetry below the energy gap of Z2 charge, then have non-trivial emergent symmetry, then now have a bulk, non-trivial bulk. So therefore, when people say there's the symmetry in the gauge theory, it's very important to specify the assumption which excitation you assume to be very heavy, and then one can make a statement. If every excitation are interacting in play at the low energy, then the gauge theory have no symmetry.
That's right.
Yeah.
So I have another question. So categorical symmetry is characterized as, topological order in one higher dimension.
Yes.
But do we know the, mathematical, object to, characterize the topological order in generic dimension? Like, because in higher dimension, there will be various kinds of.
Exactly. Yeah. It's difficult. And so next Tuesday, I'm going to give a talk in IBS and about some attempt to do this 3+1 dimension. And we have a physics approach. And I think Theo Johnson Fayette have this more mathematical approach, more rigorous one. And so that's the attempt to classify topological order in 3+1 dimension. And in 4+1 dimension, I don't know. Yeah. But certainly they all correspond to higher category theory.
Yeah.
And the higher category theory is still actually people mathematically are actively developing that. And there's some recent and also fast progress in this area. So you can see this physics and mathematics kind of co-developing in this area. Yeah.
So one last question. So here the other symmetry we consider discrete ones, I guess. And
yeah.
Do you have some comment on the continuum version?
Yeah, continuous trouble. Yeah, this approach have trouble to deal with continuous symmetry because of you can say naturally the gauge group for continuous group the bulk is gapless. Then we don't have an energy scale separation, and this holograph picture breakdown. And it's an open question. It's a very important open question, and we wish we have something to say. And so that's one thing certainly one would consider very actively to do. From category theory point of view, for continuous symmetry, there's infinite number of representation. Means you need to consider category with infinite number of objects. And recently, there are some work for U1 symmetry when try to consider, physicists consider categories infinite objects. Mathematicians probably think it's too wild to don't consider that, but physics can do that. So there's some work. I think maybe it's doable. It's not that bad. And I don't feel this fundamental question. But however, there's one important thing. I feel that for continuous symmetry, this holographic picture breakdown. And so that's the reason we call this a categorical symmetry rather than holographic symmetry, or holographic principle, or topological holographic, something like that. Because for continuous symmetry, it's breakdown. Maybe it works, even for continuous symmetry, but at the moment, it breaks down. However, operator algebra still works. This string operator, this algebra works. You just have many operators. And just that algebra no longer have interpretation of a bulk topological order. But the algebra, this extended string operator, that algebra still works. So I think that one may be more general formulation for this kind of thing. Yeah, thank you.
Okay, so more questions on Zoom? Okay, if not, yeah, let's thank speaker again. Thank you.